All right. Yeehaw. I hit record already, but I can edit it, so it's fine.
We started in this.
Trying to figure out no, I'm hard to try. But it's still oh yeah. Are you?
All right, are we ready? Ready? We'll probably have a couple more come in. Thanks for coming. Welcome to Purdue at Westgate's first Tuesday event. If you're not familiar with it, the first Tuesday of every month, we have a knowledge sharing session like this, and then we spill out over into the second floor balcony of some networking sessions with drinks and light food. So I hope that you'll have some great conversations when we go out there. So my name is Samantha Nelson, and I myself with a couple other team members here, Morgan Tavis is the marketing communication manager, and Jason Salstrom back there is the director. So we do work directly with the Purdue Research Foundation. We do programming. We have obviously this facility that we manage. So we work a lot with the tech park. If you don't know it, you're in a tech park right now. There's about 875 employees in the tech park, about 50 defense contractors within the tech park. So a lot is going on, and you've probably heard in the news a lot about hypersonics. So that's kind of what we're touching base on today. We definitely want to be the connection point or collaboration point to help put people like Chris and his company into other large defense contractors' hands, potentially into the military's hands. So today I would like to introduce you to Chris Nielsen. He is the founder of Pluto Aerospace, and his company is developing launch vehicle platforms for hypersonic and other suborbital applications to allow researchers rapid, economical, and reliable access to suborbital flight environments. So I think he has referred to this simply as rockets on a budget. So I think he's going to be able to talk about some affordable ways. So welcome, Chris. Any housekeeping? There is restrooms that is outside out in the lobby here. The men's and women's are out in the middle there. So yourself to go there if you need to. But Chris, take it over.
Thank you. Like you said, my name is Chris Nielsen. First, I want to apologize. I looked at my phone a lot. All my presenting notes are great. I didn't print stuff before I came here. So if you're looking at my phone a lot, I'm not texting anybody. I'm just reading it all. So yeah, what I want to talk about today, actually, first of all, before we get started, out of this room, like how many people are actively involved in some sort of hypersonic test flight campaign at all? Okay, cool. Just want to know how to. Yeah, so today I'm going to talk about kind of like the current state of hypersonic flight testing and kind of a mindset I think we should put ourselves in to advance it to make it better. But the first part of this presentation is kind of go over some examples, and I kind of go over back to my history and some experiences I did building liquid-sounding rockets, and then going into how I think I can apply those mentalities and lessons learned to larger scale things to just hypersonic stuff. So I'm going to first start with a quick story. So in Colorado, there was like a T&D soap manufacturer, right? I'm talking like those $50 bars of soap with saffron in them, right? Like these. And they get viral, right? And so they had to ramp up their production of their soap rather quickly. And so they invested a lot of money in this soap facility. I'm going to $50 a show, but they invested a lot of money in the soap facility, and they're sending a bunch more boxes out. So they get a lot of complaints from their customers saying, hey, you're shipping us empty boxes. There was an issue in their manufacturing. They were shipping out a lot more than a typical failure rate empty box rate. And so, they're riding that viral wave, right? They want to capitalize on this. So they said, hey, you know what? No matter what the cost, I want to hire this team of engineers to fix this problem. And so that's what they did, right? They spent many months, a lot of money on trying to figure out how to better the system. And after a while, they came up with this giant X-ray machine. Okay, so they put this X-ray machine on the assembly line, and they were basically required somebody to stand there during production hours, looking at the screen. Yes, in there. No, it's in there, and reject it. Well, it seemed to work. A couple months went by, and the complaints went down. And then, one of the upper management was walking around the facility one day. He's like, hey, wait a minute. Our X-ray machine isn't on. And he was panicked. He said, oh, God, we're going to get a bunch of complaints again. And so he runs everywhere and tries to find who is supposed to be manning this machine. He found one of the foremen. He's like, hey, why is it? He's like, sir, this machine hasn't worked since you bought it. It's clunky. It's expensive. It's always breaking down. And we just decided to stop using it. He said, why? But they thought, why haven't got any complaints thanks to boxes for machines? He's like, well, sir, we just put a fan on the assembly line. And if the box is empty, the box just blows off the assembly line. Okay. So this is a pretty generic example of a really simple solution to really, or maybe seem a really complicated problem. Right? When you have an urge and a rush, sometimes as engineers, our first thing is let's create a model, let's do something crazy. And let's get all these requirements set on us when we don't really know the requirements. And sometimes we have a bunch of requirements, other people, and we're on a time crunch and there's a lot of things happening. We end up with a giant X-ray machine, right? But really, in reality, all we need is a fan. Okay? So keep that in mind as I go through this presentation of how can we think of hypersonic testing, right? We're in a time crunch. We're putting a lot of money at it. But are the solutions we're proposing right now an X-ray machine or a fan? And what's going to be more beneficial to us in both the near and the long term? So I'll talk a little about myself real quick. So I grew up in Tampa, and in my boyhood home, there was 2 oak trees behind my backyard, back outside my window, and I could actually see the space shuttle launch from the 2 oak trees every time they launched. That really got me super, super excited about space. It was far enough away to be magical, but close enough to really be, I guess, to really be exciting, keep me really engaged in everything. So I begged my parents to join this after-school program. We launched a little rocket, and we're giving the countdown, and the lady running the program gave me the controller, and like something switched. Where I was, okay, this is what I'm doing. I'm doing sounding rockets. This is the thing I'm doing. So I started with the little small rockets. Right? I think everyone did this at one point, the small Estes rockets, and then parents like, okay, this is full phase, and they get a little bigger, and they get a little bigger. And then, and they got a lot bigger. So my grandfather had a machine shop in his garage. And so in the 8th grade, I was out in the machine shop turning things. I was using lathes. I was using not CNC before that. We were using mills, we were using lathes. All these pretty basic tools. So I like to say I grew up a mini machinist and was trained to be an engineer afterwards, just kind of neat. But we started building these larger rockets, building all these cool things, and I was really proud of myself for making, putting a fin in a bracket and making a fin can. I was so excited, and I was just really trying. But as we spent a lot of time out in the machine shop, he taught me a lot of lessons, not only on general things, but like just constant machining. Right? You always have the example of the machinist and the engineer never getting along with each other. Right? The machinist think the engineer has no idea what he's doing, and the engineers think, why are these machinists not doing what we want? Why can't they do a 6D operation or whatever? And so that kind of influenced my way of thinking and how I approach testing and whatnot. From a basically, what can you do with the tools you have available? If the tools you have available are really simple. And we sent people to the moon using slide rules and very, very, very remedial and archaic CNC lathes. Why can't we do the next step? So, and that's the rocket that ended up with that. So that'll happen, right? And this, in going into Purdue, I was really obviously excited to win rocket teams. That's pretty obvious. This guy's won rocket teams at Purdue. When I got to Purdue, there was no rocket teams, which was kind of disappointing. And I said, hey, I'll start some. And so the first 2 years, we had teams set up. Everything was going pretty well. We did some NASA competitions, we did some spaceport competitions, putting all these different types of rockets. But the reality is, it was a dumpster fire. I couldn't lead for anything. I was trying to apply amateur rocketry principles to engineering. It didn't mesh well. It was really just a mess. So, after 2 years of that, I was getting ready to drop out of Purdue. I was like, okay, I'm done. I can't, the grades aren't doing well. All the rocket dreams are falling apart. What do I do now? I'll just go home and be a psychologist or something. I'll go back to Tampa. But a snowstorm kept me in from going to my advisor. There was an ad for a liquid sounding rocket competition. And that's what kind of started all I have to talk about here. It said, hey, if you can build a rocket with a liquid oxidizer and liquid propellant, you launch that to 50,000 feet, we'll give you $100,000. That sounded cool. Didn't matter what an injector was or really what anything was on a rocket like that, but it's, hey, let's do it. Cool. So at the end, we took that 5-person team, ended up with a 300-person juggernaut of a team. We now have students doing their own liquid, solid, hybrid, any type of propulsion you can think of. We have undergrads actually developing their own systems and firing, doing all this stuff. It's not the dumpster fire. I don't know why I didn't put a pic of that, but it's really cool. But as we built that rocket, we had 18 months, all right, and taking a bunch of undergrads with no idea what the hell they're doing to building a functional fiber-propellant liquid rocket in 18 months, nearly impossible. But it's almost kind of similar to what we're dealing with now, right? We didn't move. We didn't have any idea what we're doing, but we know what we wanted. And we kind of knew what some boundaries were, so we went at it. So we're really super excited. And the first thing we were worried about was tanks, the size of this rocket. And so we had this problem, we had a bunch of excitement to this problem, so let's solve this rocket problem. And so what we did, we spent about 3 of those 18 months taking all this fancy code, trying to optimize the vehicle as best as we possibly could. We were trying to solve the problem to the 10th decimal point. We were going to get it exactly right. We went to our advisor, hey, Scott, look at this code. And he's like, that's cool. How big's your rocket? Well, code, we got a code that's going to tell us. Okay, well, what does it say? We're not really sure yet. He's like, hey, after a few months, I said, listen, don't come back to my office. Don't come to this lab again unless you give me a thrust and a weight. And that's when it's kind of a light bulb, the dog. It's like, okay, are we designing a fan? Are we designing an X-ray? We need to take an X payload to X speed. Do some basic 101 rocket equation stuff. Okay, you need X amount of propellant. Oh, look at that. Cool. You need that can fit about this volume of stuff. Cool. What's next? Do we need these fancy, unheard of alloy tanks that we roll and weld and machine to every grams off? Or thinking back to the experiences I had in my grandfather's shop, it's a piece of pipe, okay, right? Do we spend the $10,000, $15,000 to get every gram off? Or do we just spend the $200 to get a pipe and put it in a lathe and demo it and still meet the same requirement? So that kind of taught us, like, hey, listen, if we're trying to solve a problem or to find a problem, we know what we're defining, right? And that doesn't mean optimizing. So the next thing I want to talk about here is how do we launch this thing? Well, with a liquid rocket, you need 2 valves. Those 2 valves turn on, I'm going really fast, I'm sorry. The 2 valves turn on the engine to make thrusting have the rocket go up. Well, okay, so we get one of those. Well, that's when we learned that valves are expensive. 2 valves are 15 grand each. And we're like, okay, well, our budget's $2,000. That's not going to happen. So how do we solve this problem? And we probably spent, well, we spent about 13 months trying to figure out how to fix these valves. I have a laser pointer. I'll just point it here. We ended up coming up with that. So we couldn't, this side note here, this yellow thing here, this stem goes to a valve. That's typically what's used on a ground system. You're testing any sort of system with fluids, just a ball valve with an actuator. Well, you can obviously see this is 14 inches. We have a 6-inch diameter rocket. We can't necessarily fit this to there. When we thought about using it as fins at one point in time, could we just use that? How much that X'd out? But we spent a lot of money, a lot of time doing R&D in order to fix this valve problem. And eventually, we ended up saying, hey, there's a little bracket here. What if we just take that bracket off? So when the actuator actuates, the rocket takes off. This long part decouples from the valve. That's what we did. So we're able to save a lot of weight, a lot of extra things, and it worked. One thing we didn't know though. So these valves take about 0.3 of a second to actuate, but your rocket only needs about 1/10 of a second to get off the pad. So that's fun. When your valves don't open all the way. That 0.2 of a second cost us 100 grand in prize money because the rocket took off too fast. But hindsight, you look back at it, it was like, hey, what could we have done better other than doing this? When we were exciting and kind of giving an overview of what the market was, what's out there, we didn't understand everything that was out there. And we didn't understand that utilizing commercial technologies that are already existing, yes, they're going to be a little more expensive than we perceived that they're going to be. These valves were, about 5 grand each. I ain't counting all the R&D work they did, but we can get a valve like this for 4 grand. I mean, we would have done the same thing, but no valve and anything fancy. But we just didn't know. So the second lesson we learned, utilize commercial technologies that are already out there. But even before that, you really have to take a deep dive to what is really out there. Right? Just because you've been in a position for a while and you think all your vendors have their things. The reality is there's a lot of different vendors out there, and that one vendor may have your golden thing. So don't tank a whole project for something that may already be out there commercially. And the last thing is our ground support equipment. So this was really fun. So the fuel was LNG, and LNG, unbeknownst to us, is really hard to get macro bulk. You can get it by the millions of gallons, that's not a problem. But getting it, 50-gallon drum of LNG is near impossible. And so we had spent, I don't know, the entire project assuming that we can just go pick up LNG. Because our launch site said, hey, yeah, we have LNG's fine. We can do that. Well, it turns out like a month or two before we were to launch, they didn't have LNG. They had a door that could potentially hold LNG that they let us borrow. In order to get the LNG, a critical part of the rocket, it would require 220-somethings to carry this gigantic LNG door in the back of a pickup truck to maybe 6 hours one way, to load it up at maybe some gas station that may have LNG in it. This was a major problem. I was that guy that drove 18 hours trying to find LNG. But we learned that when we're building the system, we can't just, a list of requirements is great, especially for the spec of like the launch site. But when you're designing the system, if we would have known, hey, it's impossible to get LNG and microbulk to begin with, but it's even harder to get it when the launch site is an hour from the middle of nowhere, that would have influenced decisions. So the third lesson we learned, take the design from the beginning all the way through. Don't assume the bullet points are great, but go talk to somebody at the launch site, get an idea, get a feel, look at the bridges. Can this fit in here? Weren't they about to go on the bridge, but little things like that really guys. And of course, I literally spent hours talking about this project. It consumed 3 years of my life. But those were some of the 3 big takeaways we took from developing this liquid biprop sounding rocket. Now, what the hell does this do with hypersonics? So, there's 2 big problems in hypersonics today. Some of you are probably familiar with this, but getting a flight test of anything hypersonic is just too cost prohibitive. Right? That was in the RFI that Crane sent out back in January, right? It's just too cost prohibitive. How much cost prohibitive, you may ask? Well, I mean, it's done one article, right? It was $100 million for a hypersonic test development program. That was for one thing. Imagine if every time you turn on a wind tunnel, any subsonic wind tunnel, it was a significant event, they wrote a news article about it, right? That would be insane. And the fact that, the traditional ways of doing things is causing a price tag of hundreds of millions of dollars. It's not every case. I'm not saying every hypersonic flight test program is not $1 million, but they're not cheap, right? A university could not pull that off. That's some university's endowment, right? That's not gonna pull that off. So, and what's even crazier is that, Rocket Lab will take you to the moon for $10 million, right? SpaceX gets you to orbit for $1 million. It takes $100 million to get to the speeds and the altitudes that we got back in the 60s, right? It hasn't caught up. It's kind of sad, actually. So, it's not sustainable. And I was at the University Hypersonic or Applied Hypersonic Consortium in Huntsville a few weeks ago. All these researchers and professors standing up there, and obviously 80% of them made a comment saying, "Yeah, we can't get on a test, right? We can get some data on a test, maybe in a couple of years, hopefully, or if they did get a test, it's a once in a career thing." I mean, that's terrible. These professors are working, and students working their entire careers to get one flight test, and maybe if they dream hard enough, that's ridiculous. We need to obviously lower the cost. It's kind of an understood thing. Sorry. I'm very optimistic. But not all programs are like that, though. The Bolt program was out of Johns Hopkins, I believe, the applied physics lab. Basically, what they did, they took a surplus sounding rocket that NASA's been launching since the 60s, put a steel wedge on it, essentially, and flew it. Right? The whole project was $6 million. They got a flight, I think they had 2 flights, and they got some awesome in-flight data for $6 million. That's a steal compared to $100 million. So that should be it, right? I mean, if this $6 million, everything should be great. Everything's fine, right? That's not the reality, right? These sounding rockets are awesome. They really, really are. They allowed us to do so much testing, especially back in the 60s, and they're making a resurgence. You know, Congress back in 2010 basically wrote the law, hey, use these more often. And that's great. They launch about once a month out of Wallace, and they're great. That's all I really can say about it, right? They're awesome. But if they're so great, why aren't we using hypersonics? Well, these sounding rockets is a solid component. What does that mean? That means what you get is what you get. You can think of it as one flight profile, one trajectory. They're also in parabolic trajectory. So, you know, they're only going to go up like this, which isn't bad. It's really cool. It's really great if you're using like a telescope to get down the atmosphere. It's awesome. But you know, hypersonics. Actually, I'll skip a couple slides. This is awesome. What we really need is down here, right? We don't need to go we can go hypersonic speeds in space. That's not what we care about. We want to go those hypersonic speeds in the atmosphere to meet the requirements of the systems we're building. So that parabolic trajectory is great, but they only get like maybe 10 seconds of actual data. So you get $6 million, 3 years, 10 seconds of data. Awesome. That's crazy. So what they did, it was successful, it was great, but from my understanding, they couldn't get funding for a second one. Even at $6 million, it was too expensive to. Just like even all the hardware is there, even though they did it, they learned all these lessons learned, and it was really successful. They couldn't get another flight. And the sustainer, by the way, wasn't even the American rocket, from my understanding. I believe they had some work out for the Australian space station. But yeah, that's where we're at. Sounding rockets are great, but they're not great for hypersonics in terms of trajectory. But they are amazing for ease of access, cost, and I kind of went over the flight path graph. So, sorry, I skipped the slide, which is awesome. So, to compound this even further, right? If you only can fly once a month, you're not getting away with that fast. So SpaceX is kind of synonymous now with fail fast and learn. Right? These guys are building these gigantic rockets, blowing them up every week on purpose, learning how they do them, and implementing those ideas. They're getting from nothing to this monster orbital vehicle in an impressive amount of time. What if we can have that amount of change for hypersonics? So it's a game changer, right? We can't fail fast and learn because we only fly maybe once a month sounding rocket, but truly every 2 or 3 years for anything else. Think of how many breakthrough technologies have been sidelined because it's too risky to put them out once every 2 year flight. Think how many technologies that are maybe just too risky that could really maybe alter the way we think of hypersonics are put aside because it's too expensive. It's too expensive for a project. You can't do it. You have to go the low risk path. I personally don't think we're going anywhere back. If we really want to catch up and then leap ahead our peers, I don't think we're going to do that by being, conservative with how we test. We have to test. We have to blow things up. We're going to burn things up. We're going to spend money on flight tests, and the experiment's going to fail, and that's okay. I think we're going to learn more failing than we are succeeding, because if we're just spending, $6-10 million a flight to pat ourselves on the back that our model was right. Great. Let's learn something new. So, sorry, very small things. So let's build our own web platform. Yeah. Some of you are gonna hate this, some of you are gonna love it. So we know sounding rockets are cool. We know sounding rockets are cheap. But we have a blank slate. Let's figure out how we can test more payload, a higher cadence, for a lower cost, without making an X-ray machine. What's our plan? How about we start off with an airplane? The 747. That seems to work. But let's instead take two 747s and strap them together. I think some of you know where I'm going with this, okay? And with those two 747s strapped together, let's design a rocket plane to under those two 747s strapped together, okay? And let's have that plane have gears on it to go back to a launch center. So after all of this, it works, right? We can take off and land. We can launch somewhat regularly. Has the word rocket in it. That's always a plus. And it's only $5 million a flight, and we get to have a couple pounds of payload on our vehicle. And don't worry about if one of the planes is down for maintenance and the whole thing has to stop, because that plane's really the only option to get anywhere. So that's kind of a major thing. This is some people solutions hypersonic testing. Let's add a bunch of planes, a bunch of rockets, and have it returned to home. And that's cool, and it works. But you're only going to get a few pounds of payload. And there's a couple other widgets to worry about in order to function. So let's not do that. Because to me, that's another X-ray. What's our thing? Well, as I mentioned before, we want affordable, reliable hypersonic testing that catch up and leap ahead our peers. It needs to be capable, high cadence, affordable, and it has to be simple. It has to be simple. If it's not simple, it's complex, and complex equals money, and money equals it's just going to found on each other. So we need tailored payloads in a variety of relevant environments. Okay. My slides are out of order. I apologize. Just flying a widget on a space plane will give us a lot of data. But what are we going to do with that widget after? Are we building for what our requirements are now, or for what our requirements are now and the need for tomorrow? And we did that, or we can go over that. So what if we had a sounding rocket that could do those four things in the previous slide? Well, that would require developing our own engine, right? Developing a liquid engine. That's pretty expensive. But back to what I was saying earlier about just knowing the market is out there, right? There's companies that sell ready to go plug and play rocket engines at costs that would keep you up at night. They're so inexpensive. How they do it, math? It's impossible. So, since companies like SpaceX and Blue and name any other startup, right, are launching so frequently now, all of the components used to be very, 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 very expensive to support these engines are benefiting from the economy of scale. So all the support equipment for an affordable engine like this are lowering down. So we're able to develop a sounding. You could develop a sounding rocket as a liquid component and utilize all of the what's called price breaks, but the affordability of all these components and subcomponents you're doing, which is pretty neat. So, I'm sorry here, I should have printed this out on paper. Yeah, let's go to this next slide. So, perfect is the enemy of good. So we need this technology now. But waiting for perfection is going to put us behind. So we need something that meets both the requirements, but not the retirements of today. But these price breaks, all these components and engines don't make this significant work. Or we have to build. We have to build it in a way that makes sense. If every time we build a rocket requires a 2-year lead time, right, with a material and an alloy that's hard to pronounce, we're not going to get anywhere fast. Relativity does this in a really interesting way. They're just 3D printing the whole rocket, which is awesome. If I had access to this, I don't know if it would be awesome. But that's not going to get us anywhere far, right? They basically say, we are going to develop this whole printer. We're going to go one way. That's cool, but for everyone else, we can't, unless you want to develop a new manufacturing technology, utilizing something like this for a new hypersonic vehicle isn't going to work. So, we have to think of what we have. And thinking back to what machines are available to us, if we can utilize forging, right, partly 3D printed things, and we use those at scale without any additional tooling or manufacturing process, we can not only build a lot of them, maybe you do more than a monthly cadence, but you do a weekly cadence. You build a lot of them, price things down more. All going back into affordability. And then lastly, of course, recovering these rockets is great, but again, that's another requirement. But if we can recover these things, if you're building an act, if we're utilizing all these commercial technologies, they're becoming more inexpensive in the economies of scale. And we build these things to fly once a week. And we use the economy scale of that. The idea with the cadence, right? And we can recover these things. We could potentially get a sounding rocket to send these payloads to relevant environments at a cost that a professor or researcher at a school could do, not monthly, weekly, but yearly, right? If we can get that cost down to a point where the professors at these conferences aren't just sad talking about their dreams of flight, think of all the cool stuff we'll be able to unlock, and all these crazy technologies we can unlock. So what's next? I talked a lot about affordability, cadence, building environments. So I have to put Pluto real quick, right? So if we can build a sounding rocket, we can put things in relevant environments at cadence, at scale, we're good to go. So at Pluto, we're developing a little video here. We're developing this. It wants to go. Perfect. Okay. It's a by-prop, quick sounding rocket. We launch with no crazy planes, no crazy launch platforms. We take a turn, we can get development environments from 80 to 130,000 feet. We can go over, take any payload, widgets, full scope glide bodies, to speeds over Mach 5, over 60 seconds, and recover with a parachute. So it's kind of like a second generation sounding rocket. We're not saying that these sounding rockets that NASA's used forever are bad. They just don't fit our needs right now. But if we can refresh them, bring them back into use technology that's available to us now, we can get all the cost benefits, all the usefulness from the sounding rockets, but just modified for hypersonics. Like I said before, we can take 750 pounds over Mach 5 for 60 seconds, utilizing just the commercial technologies that are available right now. That's of any additions or modifications to the engine, right? That's just what we can do right now. And like I said, easy to find payloads. So we do widget, you want to do a subscale glide body, that's fine. It's exactly what the sounding rockets at Wallace are doing right now, just upgraded for today's needs. So Pluto's been pretty busy the last few months. We're actually we purchased an engine from Mercy Major, that's coming in pretty soon. We sent a space attribute from NASA Wallace to the launch pad. We're working on getting a launch pad at Wallace to fly by the end of next year. I've lost another slide. And so, that's kind of the end of my talk. I'm sorry, I kind of lost a few slides in the beginning. I think when I got updated when I came here, it put some things out of order, so I apologize for that. But to summarize, right, the future hypersonic testing, high cadence, affordable, and capable for open environments. The way I think we do that, instead of developing brand new crazy systems, a lot of moving parts, let's just build a new generation of sounding rocket that's worked for the last 60 years. So, and one note about that soap is actually $50. I wasn't lying. It's some pretty expensive soap. So, yeah. So, thanks.
Anybody have any questions?
How many launches have you?
Our first launch will be next year.
And I am not in aerospace, but look at your website, look at your launch, you look at proposing that launch.
No, we're doing a launch today.
Why not something like even like Carolox or even
Well, Carolox is also an option. So we based our requirements off the hat. So we didn't want to develop an engine because it'd be too costly. So we kind of like I was talking about before, we looked at what's available in the market right now. Okay, the had. Does it meet all of our requirements? Yes. Does it meet all of our desirements? Not quite, but it will work for a first vehicle. So
with your first launch being next year, Rocket Lab just demonstrated recovery by helicopter.
Right.
But do you have a test vehicle which is able to test recovery options?
it'll be the first vehicle for next year. And all of our customers so far, we're not quoting the recoverable vehicle. We're in the assumption we won't recover it, after a handful of flights. So we're gonna, part of it's also learning for us too. We'll learn how to slow it down too, slowing down something like that. And that's kind of hard. It's not usually a problem. Hypersonics have, they don't usually want it to slow down before it's done flying. So
Shoots over react.
yeah. Oh yeah, parachute. Oh yeah, we're not just shooting out a parachute out. We have a system of grid pins right now. It's kind of our current working. Slow down a little bit. Yeah.
What is your cost for what we, at lab, for lab, okay. When is underlying
So we're not releasing publicly what our costs are. However, it would be the equivalent of a very full New Shepard flight.
So what's the estimated number that you, what's it?
Yeah, that's kind of our max. If the customer wanted to test some sort of ramjet, right, we can take up to 1,500, I believe, to Mach 3. But that's kind of, I don't think it's gonna be a big thing. Yeah.
Your launch site you specified as Walrus. Is there any specific for choosing Walrus as a launch site as opposed to other more quote unquote conventional rocket launch sites such as Cape Town or Vancouver?
So lots of openings. It was a big thing. But also, I should also know we haven't signed an official lease for a concrete yet. We're in the process of doing their upper level reviews and whatnot on the track for that. But they also have a lot of facilities for like secret assembly and whatnot. And the personnel there, since they've been building these rockets since forever, there's a lot of corporate knowledge there that NASA is willing to share and engage with us as we put it on the line.
How big is Pluto?
So we're located in West Lafayette. We're currently 5 contractors. We have raised a little over $300,000 over the past 8 months, and we're getting ready to raise a lot more money than that to build up to 15 by the end of the year. That's one cool thing about these rockets. It's like we don't need a team of 200 to build this, and that's not just an estimate we came up with. This is also demonstrated from previous NASA sounding rockets and other companies that have used have this before. So really more than 15 eventually, but we think it's a good number to get pretty far for now. We're still really far.
So the older companies, Hypersonics use it.
Yes. Yeah. And usually the question is, well, why aren't you only doing Mach 5? Like Mach 10 is cooler. And it's like, well, you have anything Mach 5 right now. It's kind of our response, like, okay, cool. We do want to go big, however, we are focusing all efforts onto this one thing. We're being very, very deliberate, not saying, what's the next big rocket? I want to focus on this one.
I'm kind of curious, like, what are the ranges of payloads that you expect to have on the rocket? Like, all the way down to like small little experiments, all the way up to like ramjets.
I think the picture I showed, I think we're back to it, with Bolt, I bet that's, oh, that was a long while ago. I think this is more what we're gonna see. We do have a configuration for multiple widgets at one time. However, we think the chances of success, or especially for the first few flights, will be much higher with a single user body like this. Yeah. Oh yes, sorry. I believe that's 18 inches diameter on the bottom. Yeah, so this is about the size of a person. This is a 700-pound piece of steel. Yeah. And it was called this is the Bolt 2 APL. They have a really good paper on it. We get some really useful data out of it too. It's a shame they couldn't fly it more times. I think stuff similar to this even before Bolt 2, but I mean, just the most recent thing. One more.
What other people like use it or have interest?
There's a lot of demand. I can't go into specific shit.
Could you fit in like a communication payload,
Hmm?
sensor, or things like that? So
Oh, absolutely.
focus on kind of like they do with.
Yeah, absolutely. Yeah, absolutely. That's hopefully a goal. If it was just a single user doing a single antenna or whatever, honestly, Stratolaunch is probably better off for that. They're more suited to just widgets. Like I said, we want to be able to do a suite of widgets, but I don't think it'll be cost effective for the user just to be the only person flying a few pounds in the vehicle. Hopefully, we do call it a ride share. Will be more than competitive with others. So, all right, thank you.
Thank you, Chris.
Thank you.
We appreciate Chris coming down here from West Lafayette, so I know it was a drive and he'll get back a little bit late. One good thing that I thought was amazing was that he was from Tampa. He came to Indiana to school. He stayed in Indiana. He's keeping this technology in Indiana, so that's what we'd like to see.
Yeah.
And so we appreciate you coming and doing that. Very interesting.
Yeah, it makes sense. You know, I had a couple of friends that did their own startup. They moved to LA and they were out of cash in 4 months. They raised $600,000 out of cash in 4 months. That's not a way to. It's not the best place to go. So
you can talk to Chris directly. We're gonna go outside, like I said, on the second floor balcony. There's some light food and some drinks available. You can certainly ask him more questions. This is being recorded, so you will all get a copy of the recording as well as the copy of the presentation. We do want to thank SAIC because they're the ones that sponsor this event for the food and drinks. So we definitely want to thank them. They're a pivotal partner within the tech park here. So we can all go out there. So thanks for coming.
thank you.